All right, so hello everyone. How are you doing? It's quite hot today, and I was wondering that you might have attended the conference yesterday and the workshops as well. So how about we kind of jazz up the energy in this room a little bit by doing what I call the open web stretch. So I'm going to request all of you to kindly stand up. Please bear with me for a few minutes. Cool. So this is how the open web stretch goes. So first of all, we reach up there to all the open source streams. We reach high up there. All right. We come back down and touch the grassroots. We come up and we blow the winds of change. Just energize ourselves a bit. Then we reach on the front and shake the money tree for fundraising. Give it a good shake. All right. We lean left to avoid the NSA. We lean right to avoid the FSB. And then we go all around to avoid the NSA and FSB. Awesome. Thank you. So before we go any further, I would just like to know the demographics of this room. So how many of you are data engineers or data scientists? Okay, awesome. And how many of you have worked with databases before? Okay, which ones? MySQL, MongoDB, okay, Influx. Okay, so we have a really good proportion here. So today we will talk about a couple of topics, which includes time series data, what it is, and how its workload differs from other forms of data. We are going to talk about different use cases where time series data is being used quite widely these days, how CrateDB helps in dealing with machine data, and what are the technical aspects of the database that make it so efficient to handle the workload of Industry 4.0. Then we are going to talk about CrateDB running on Microsoft Azure and the different things you can do with it. We'll also take a quick look at how you can launch your own CrateDB cluster on Azure. And finally, we will do a case study about a smart factory that we are working with and do some querying on their machine data. My name is Tanay, and I currently work as a developer advocate at Crate.io. And I love working with time series data, especially machine and sensor data. I'm a tech speaker for Mozilla and volunteer to their various projects in my spare time. And I have written books on Firefox OS when it was still a thing, building a virtual assistant on Raspberry Pi, and web-based virtual reality. I'm also an software innovator in the field of IoT, and towards the end, I will share my email and Twitter handle. So if you have any questions after the event, or if you'd like to collaborate on a project, please feel free to get in touch with me. I'll be more than happy to collaborate. So let's get started. So before diving into the Industry 4.0 use case, let's talk a bit about time series data. So the million-dollar question, what is time series data? And most importantly, how does it differ from other forms of data? So to answer this question, imagine a sensor. And this sensor is sending streams of data over a period of time. And if you were to plot this data, one of the axes would be time. And as compared to some other workloads, this data is not usually added as an update to the database. So time series data is added as an insert, and this is the primary way how the workload is being handled by the time series databases. So time series databases introduce efficiencies by treating time as a first-class citizen. And this allows you to delve into all the aspects of your operation, having such a rich amount of historical data, such as analyzing the past, monitoring the present, and analyzing the future. So now that we have a slight idea of what time series data is, what it looks like, let's play a short game that I like to call Time Series or Not. So does the data visualized by this graph denote a time series data set? Time series or not? No. So here we are measuring the production metrics against different countries. We have no aspect of time here, so no. Time series or not. So here we have an example of time series data. Last one, time series or not. Yes. So awesome. Now if you take an abstract look at the use cases of time series and the kind of data that is generated by these use cases, you can roughly categorize them into two types. So first of all, we have IT and system monitoring. So this can be termed as the traditional use case of time series databases. And this can be characterized through tens or hundreds of metrics and sensors, real-time write queries, variety of complex queries, and data volumes that usually fall in gigabytes. And InfluxDB is a really good database for this category. And then we have industrial sensor data. And this is an emerging sector that I feel has not been talked about enough. So this is characterized through hundreds of thousands of sensors or metrics and real-time queries that are under highly concurrent load and must access hundreds of gigabytes to terabytes of data. So CrateDB is an especially good fit for this category. So there are some other characteristics that separate these two use cases, like the projects that fall under the former category, the data that is being handled by the database and the data that is being visualized in dashboards is often not that mission critical. And the projects that fall in the latter category are often mission control projects, and this data kind of gives valuable insights that gives guidance for real-time actionable insights on the production floor. And it's a machine data world, and machine data means an explosive growth. So in 2018, there was a boom in the number of IoT devices and their use cases. So there was an increase in the use of IoT devices and sensors in different contexts, such as smart cities and smart factories, which is being referred to as Industrialization 4.0. The total number of IoT devices is moving towards 20 billion by the year 2020, and every second, another 127 devices are being connected to the internet. So just to get an idea of how drastic this data is, consider an example of Boeing 787, which generates about half a terabyte of data during a single flight. And if you talk about the plastic manufacturing industry, for example, there's a wide array of data being produced per items that are being manufactured. So if you talk about a bottle, for example, there's data that is being produced per production line, and these factories typically have about 10 or more production lines laid over the entire factory. And this data is being generated by more than 900 sensors, different kind of sensors laid over the production lines. So there's data basically being produced on billions of bottles. And this particular company that I'll talk a bit about later, this has about 180 factories in 45 different countries. So let's move on and talk about CrateDB briefly. So have anybody used CrateDB or have heard of it? None of you. Okay, so let me start off by introducing CrateDB and going into the heart of the honeycomb and just take a look at what makes it stand apart from the various other databases in this segment. So CrateDB is a new kind of distributed SQL database that is best suited for industrial time series data because of its ease of use and its ability to work with terabytes of data with thousands of different sensor data structures. And CrateDB is quite simple to install, so you can spawn off an instance by a single line on your terminal or on Docker. And CrateDB uniquely combines standard SQL with NoSQL benefits. And it operates on a shared nothing architecture, which kind of gives it an edge over database systems like Postgres, for instance, which are operating on a master-slave configuration. And the various nodes that are present in a cluster coordinate with each other seamlessly, and the execution of write and query operations are distributed throughout the various nodes that are present in the cluster. And it is ANSI SQL compatible, including joins and Postgres via protocol, which allows integration with tools like Grafana really easily. And it gives you a kind of ease of use and prevents lock-in because you don't have to learn new query languages like InfluxQL or MongoDB's query language, for instance. CrateDB supports SQL with full-text search, JSON, time series, geospatial data, and even blob tables. So this architecture is quite well suited to containerization, meaning that a cluster that is running on Kubernetes can be scaled up or down with a simple kubectl scale command. So that basically scales down the operation where you have to increase the size of a cluster from weeks to minutes. And operations like sharding, rebalancing of data, or clustering as the size of the cluster increases is automatically handled by CrateDB. Now, CrateDB has columnar caches for real-time, in-memory SQL query performance. So real-time databases, what they usually require is all of the data to fit in the main memory. But that kind of has limitations on how much data we can actually manage. So our solution for real-time performance without data volume limitations was to implement memory resident columnar field caches on every single node. So the caches tell the query engine whether there are records on that node that meet the query criteria and where the records are located. And this is all performed at an in-memory speed. So distributed query processing also contributes to the fast performance, and we have a query planner which makes really smart decisions on which nodes are most suitable for performing aggregations or joins. So CrateDB excels at handling the velocity, volume, and the diversity of huge Industry 4.0 workloads. For example, industrial sensors can often increase the frequency of measurements that they are taking if the threshold values have been passed. So if the rules detect that, okay, the values that were supposed to be at X and it's exceeding X, that can cause huge data ingestion spikes. And CrateDB is able to handle these spikes in data ingression, meaning that your reporting and querying won't fail just when you need them the most. So speaking of smart factories, our motto is put machine data to work. And every day, millions and billions of data points are being generated by sensors, smart factories, and health industry, which is our Industry 4.0. And data from Industry 4.0 needs to be ingested in real time. And this data tends to be complex and can be in many different forms. So this data gives us valuable insights which can be obtained by performing analytics on the data in real time. And queries like aggregation, time series analysis, along with machine learning or predictive analytical models are often applied on this data. So the insights that are produced by these analytical operations can often be used to take action to improve the efficiency and functioning of these various industries, hence causing really big, significant cost reductions. So the differentiating factor that should be kept in mind as opposed to other time series workloads is that these queries are under highly concurrent load. Think of stream processing or machine learning, and must access gigabytes to hundreds of terabytes of data. So this fire hose of data needs to be handled in real time, and we need to be handling in real time so that we can take actions on the factory floor on that. So let's talk about the next layer of the honeycomb, which is built on the top of the core CrateDB technology, which is CrateDB Cloud, also known as CrateDB Azure. So do we have any Azure users here? None? Any Azure users? Oh, just one? OK. I'll take that. So CrateDB is a scalable SQL cloud service hosted on Azure, which is operated 24/7 by experts at Azure Iot. So it is quite ideal for industrial time series data processing and other IoT and machine data specific workloads. So it has real-time query performance for partitioning, parallel processing, and in-memory columnar indexes. And it also has really good Azure IoT integration with built-in interfaces to Azure IoT Hub, MQTT, Postgres via protocol, REST, JDBC, and a native .NET Core driver. So let's take a quick look at how you can launch your own CrateDB cluster on Azure, and then we will move on to our study of a smart factory. So let's take a quick look at a command which is called crowd. It's the command line for handling CrateDB Cloud. So you can install that using pip with pip install crowd, and we have much more information about crowd available on our website. So you can log into CreateDB account using Crowd Login, and this will open up a browser window with which you can either log in, or if you don't already have an account, you can sign up for a new account, and you can do that for free. So once we are logged in, we need to create an organization for the user. And this organization basically holds the projects, which in turn hold the clusters. So we would create this using crowd organizations command and give it a name. And I just realized I misspelled Sophia, so apologies for that. So this will give me the organization ID as the output. And now we need to create a project which will basically hold our CreateDB cluster, and we do it with the help of crowd projects command and give our project a name and the organization ID that we got from the output of the previous command. So this will give us project ID as the output. And now we can finally deploy our cluster with the help of crowd clusters command. So we have to supply it with various pieces of information, such as product name, tier, project ID that we got from the last step, cluster name, version of CreateDB that you want to run on this cluster, and last but not the least, username and password. So this will deploy the cluster and give you the fully qualified domain name on which you can access your cluster. So since it takes a few minutes to deploy, I prepared this cluster in advance. Let's take a quick look at it. Are things visible in the back? Is it readable? OK, perfect. So this is the CreateDB cloud interface. So here you can see we have deployed the cluster on Microsoft Azure, and we have a single node cluster running here with 3.3.3 version, and we have other different options here, such as we can see some basic metrics about the cluster. We have logs, we have snapshots that are taken every hour, so in case there's a catastrophe, you can restore that to a previous state. Let's take a quick look at the admin UI now. So this is what the admin UI of CreateDB looks like. So first of all, we have some basic information, such as number of nodes this cluster contains, health, total number of records that are contained, and so on. Then we have a place, which is a console, used for making queries. Then we have a section for tables, which basically shows how many records this table contains, how many configured shards are there, the schema of the table, and so on. So let's take a quick look at this. So this is a new cluster that I created, and I just imported some public tweets. So we have some data here. And as I mentioned earlier, that CreateDB supports full text queries because we have a layer of Lucene running. So let's do a quick look at the full text search capabilities of CreateDB. So let's try to find out if a term occurred in the number of, let's see how many tweets we have. First of all, we just have 1,094 tweets. So let's try to find out how many people have cursed in these tweets. How many do you think will turn out to be? Any guesses? All of them? 50%? Well, it sounds like a reasonable. OK, let's do this. 4, I'm positively surprised by that. That's good to see. So we can do full text queries with this, and then we have a section for shards, and we have a section for getting various information about the different nodes that are present in the cluster, for monitoring, for users, and for we have a help section where if you have an empty cluster, you can basically import public tweets to play around with CreateDB. All right. As promised, let's talk about the Smart Factory case study. So I would like to share with you all a story of one of our customers named Alpla. Have anybody of you heard of them before? No, OK. So most of the people in the world use their products at least once a week, be it Coca-Cola, Head & Shoulders, or Dove. And Alpla is quite well known in the consumer packaged goods market for its innovative package systems, bottles, closures, and injection molded parts. So in 2017 alone, Alpla produced over 100 billion consumer goods packages. And with over 100,000 tons of recycled plastic, it is also one of the leading packaging companies when it comes to recycling these plastic materials, also known as the closed-loop plastic economy. And we have been working with them over the past 3 years. So this is where real-time information from the production floor has the real potential to add value to 180 factories in over 45 different countries. So they have different sensors for temperature, pressure, blending ratios, and other settings that need to be really precise on every single machine. And if these settings are right, high-quality products are the result. And when these settings are off, quality suffers and the production costs increases. So I have a question for all of you. How would you imagine that malfunctions or errors in a factory floor are detected? So if you, for example, talk about, for instance, a server, there's some error, there's some set of rules probably which will send you a notification, or you have a dashboard which tells you that something is wrong. How would you imagine that such a factory used to notify people that something is wrong? Any guesses? Sorry?
5 persons?
No, I'm asking how would you imagine that these smart factories would, not smart factories, factories before that would tell you if there is something wrong with a certain machine or something. What kind of, sorry? Sorry? I cannot hear you.
Bell ringing.
Bell ringing. No, think more primitive. You're close to that though. No. Smoke, no. Not on a factory floor. Okay, so what they had was they had different production lines, and they had LEDs or some bulbs on the top. So basically you see if it is red, then there is something wrong with the machine. So imagine a factory floor with just 4 production lines, and each of these lines, let's say, have 4 machines each, right? And in this factory, they usually have some sort of visual indicator which shows if everything is working correctly or not. And in order to discover these issues, multiple people had to be walking through the factory floor, throughout the factory to see if everything is working correctly. And that was me when I learned how sophisticated their workflow of discovering malfunctions was. So one of the typical scenarios that can often happen is that a person on the factory floor is currently working on fixing the issue, let's say at the production line 1, machine 2. And once he finishes that, he walks through the entire production floor and sees if all the other machines are working properly. And that is then he notices that on the production line 3, machine 4, the light is red, so something is wrong. And once he kind of investigates that, he realizes that he needs to go back to machine 1 on the same production line, and he needs to make some adjustments there. And then the person moves again throughout the factory to see everything is working correctly. So the problem with this is the production lines in factories are laid out over the whole factory, and the distances between the machines can be really considerable, meaning that this was a really slow and labor-intensive process. So additionally, the latency that was introduced by having to walk through the factory floor meant that many products were often created defective because there were times when there was a malfunction and it was not even detected, and it took as much as 15 minutes for a personnel to come and detect that there was an issue. So this resulted in loss of quite valuable machine time and a loss of raw material as well, because defective products are being produced. So Alpla's market entry in North America in 2001 was followed by years of tremendous growth. So in 2015 alone, it was already operating around 14 manufacturing plants with more than 1,000 employees in the US. So with this growth came the challenge of hiring and training enough personnel to keep all this process running smoothly. And because modern manufacturing processes all have a terribly complex user interface. What happened was they needed a very specially trained person for every single machine on every single shift. So as a result of this rapid growth and rapid amount of data, their database performance degraded, and response time for queries got longer, and it took as much as 4 to 5 minutes for each chart to refresh itself. And again, real-time actionable guidance on the factory floor was no longer possible. So Crate.io built their proof of concept over CrateDB cloud and enabled them to drive technological transformations. So the first step was to send data to CrateDB alongside their existing SQL database, and this immediately improved the performance. And reports and analytics, again, could be generated in seconds, so that this whole process worked very smoothly. So this allows Alpla to establish a closed loop of continuous production state monitoring and process improvement on how this data is read from the machines. So I would like to share with you how the machine data from Alpla looks like, and we can do a few queries on that data. So this is the admin UI of the Alpla production for the mission control, which I'll talk about it in a bit. So we have a cluster containing 5 nodes here and about 2.9 billion records. So to understand how this whole thing works, let me take you along the flow of the data and see how it changes once it comes to CrateDB. So if you take a look here, you would notice that we have different factories sending raw data. So all the tables prefixed with raw underscore something basically denote a table, and this table is created by the data that is coming from a particular factory. So this data, for instance, is coming from the Bethlehem factory, this from Florida factory, and so on. So let's take a look at one of the raw tables quickly. So here we have about 31.9 million records of data and 10 configured shards. And if you take a look at the schema, we have a really simple table with just 4 columns. We have month partitioning, we have payload, topic, and a timestamp of when the data was inserted to CrateDB. So let's take a quick look at this data and see what it is like. So as you can see, here we have expected timestamps, we have a topic, and then we have a payload, which is basically a JSON object. And we can unnest this object, and it has multiple pieces of information in it. So if you take a look at this, path, for example, denotes that this data is coming from a factory. It's coming from the Bethlehem plant. And if you remember the diagram of the factory floor, it tells us that this data is coming from the line 2, and then it gives further information about which specific machine and which part of it is sending this data. Now, if we take a look and find some other topic, currently we were taking a look at border underscore counts. So here we have another topic, for instance, in the same column. And if we unnest this data, you will notice that it is quite different from the data that was in the border underscore counts topic. So this is possible, differently structured data in a single column, because CrateDB has the dynamic object data type. So anyways, once we have this raw data in CrateDB table, we run it through an enrichment process. And what this process basically does is it takes all this data and it splits it up and it puts it into different columns. So in case some of these data values that are coming does not have a value, it assigns a null value to it. And this does not affect the performance, unlike MySQL. And after that, we add some business logic to it, some sensor information, and all the data that are in the columns after this enrichment process are strongly typed, so that highly increases the performance of the data then. So once this enrichment process is complete, that is how we end up with the metric table. So here you can see we have a metric table with about 75 configured shards and 1.4 billion records. So now let's take a look at how this data looks like. As you can see now, we have much more columns here, and if the corresponding value for a row is not present, we have null values for it. So let's run a few quick queries. I prepared them beforehand, so I'll copy paste them and see how the performance is. So I think it was somewhere around 1.4 billion records. And here I want to run a query when I want to know if there was an alarm or a notification. I want to know from which unit and machine this notification came. And I put some constraints, like the machine should be BME 200 and the type should be alarm. So once I execute this query, I get the information that I'm looking for in just 0.9 seconds. Let's take a look at a longer query. So this is something that's actually quite used in the dashboards for reporting purposes. So here I want to know about how the performance of the factory is, if there have been some process improvements and so on, and how better to find out how much things can be improved by finding out the downtime of the factory. So here I want to know about the location line, the downtime reason, when the downtime started, when it ended, how old it was, and for how long it lasted. And I have put some constraints, like the type should be downtime. Let's say I'm going to inspect a factory at McDonald's, so I want to know only about the McDonald's plant, and some other information such as the reason should be cleaning of tool, because in the factories you often need to take down machines for predictive maintenance and so on. So let's run this query, and we again have a sub-second query, and we get information what we wanted about why the downtime happened, for when there was a cleaning of tool, when it started, how long it lasted, and how old this incident is. Let's do one last query. It's a slightly longer one. So here I want to know about the field name, the model of the machine, and number of occurrences that machine had over the last 90 days. And I have a host of different conditions here, like the type should be a molding machine, and lots of other things. And executing this results in a query which is again a 0.1 second query, and we are iterating over 1.4 billion records. And if you take a look at the cluster, you will notice that we just have 5 nodes here with about 15 gigs of RAM and 8 cores of CPU, and yet we are able to achieve such fast performance with it. And once we have this data, what happens is that we visualize it. So we can visualize, we use something called Apollo visualization for that. So you can select a plant here, the operations, and let's say take a look at plant overviews. So this dashboard basically is open in the mission control of the factory. So as you can see, we have different lines. So we have 9 lines over a factory. This is data on the McDonald's plant, and we are able to get a host of different information, like, okay, in this production line, how many incidents there have been, how many times the machinery had to be closed for repairs or for predictive maintenance, and so on. All right. So basically, when the Create IoT data platform, which is all these different apparatus built on top of CreateDB Cloud, detects or predicts an unusual change in data, it alerts a factory operator who is sitting in a mission control. And the mission control for Alpla is placed in Atlanta, US, and it actually looks like this with different dashboards for different factories. And now the operator alerts somebody in the factory floor via a mobile notification system suggesting an adjustment or repair. And now, since the employee on the production floor has real-time actionable guidance, while he's fixing the first issue, he would just get a mobile notification saying that something is up on production line 3, machine 4. And to fix it, you need to go to machine 1 and make some changes in parameters. And after the issue is resolved, the factory operator logs a note explaining what the issue was and how they solved it. And these notes are shared via online manuals across all the factories to improve knowledge sharing of best practices. And that is how we close the loop by using data to take real-time actionable guidance on the factory floor. And every plant in Alpla using CreateDB saw improvements in net equipment efficiency by as much as 90%. And every plant also saw a reduction in manual process adjustments by as much as 50%. So these were some of the metrics that they were using to measure how the performance of the factory and the working of the factory has improved. Now, reducing the number of manual adjustment also stabilizes the process and significantly improves production efficiency. So the result was a six-figure saving in 2018. So currently, there are about 2.5 million queries per day, and work hasn't even finished yet. It is estimated to increase about 18 times by the end of 2020. You can also take everything that we talked about and move it to the edge, and it is as simple as deploying a few Azure Iot Edge modules. So anybody of you are aware of what Azure Iot Edge is? Just one person, two people. Okay, so I'll give a very short overview. So let's think about the smart factory use case again. And because of the sheer volume of the data that is generated, it is quite possible at times that customers, like smart factories, would like to store the data on the edge, which is their local premises. And they do it for reducing network overhead and latency so as to come back to the actions with an even shortened turnaround time. So we recently collaborated on a demo with Microsoft which shows just how to do that. So the sample is hosted on GitHub and shows how to store machine data from OPC UA simulation servers into a single CrateDB node. So all the necessary components are deployed by Azure IoT Hub, and we have some of the following IoT modules that are deployed. So we have an OPC UA server module, which basically simulates the data that is coming from the OPC UA servers. We have an OPC UA publisher module, which kind of exposes it for other IoT modules. We have a CrateDB module, CrateDB saver module, which basically pushes the published data into CrateDB, an enrichment module, and finally the Grafana module for visualization of this data. So you can use something like Vagrant to simulate an edge device unless you have want to run it on Raspberry Pi or the AZ316's Azure chips or something like that. So the enrichment module then takes this data and enriches it, which is not that different from what we saw earlier. And this enriched data then is stored in the metric table. And after that, we can now use Grafana IoT Edge module to visualize this data, which is quite suitable for time series data visualization. Now I would like to share with you some of the product features that we have coming in our roadmap and we are quite excited about. So for CrateDB, we have PostgreSQL compatibility, and we are constantly working on improving this. Integration with various visualization tools like Jaspersoft, Apache Supersets, and so on. We are optimizing CrateDB for different connectors for different languages like async PG for Python, PGX for Go, MPG SQL for the .NET world, and for optimizing how these connect to CrateDB so that they're able to use the capabilities to the fullest extent. And we are also working on implementing cursor support for streaming ML applications, for instance. And we are also, on the cloud side of things, working on improvements to the IoT Hub connector, Grafana shipped in each region of Azure, implementation of billing so that customers can be directly billed via their Azure subscription, and finally, direct query support for tools like Kafka or Power BI. So I hope you're as excited as us for the new things that are going to come up. So with this, I would like to conclude today's session on machine data in Industry 4.0. So today we talked about time series data, its use cases, machine data for handling machine data with CrateDB, CrateDB running on Azure, how you can launch your own cluster, and finally did a small case study on how a real-world smart factory is handling machine data. So we're in this booming age of data, so why not put it to work to make our lives easier, safer, and better? And if you would like to play around with CrateDB clusters on Azure, I'll be sharing the slides later on. And I also recently published a blog post at Crate.io, which shows how to do that in a much more greater fashion. So I'll be here till the end of today. And if you have any questions, feel free to catch me. I'll be happy to converse about that. Thank you very much.
Why this choice of Azure? So I have nothing against, but...
So we do think about deploying to other providers as well, not that soon, but to GCP and Amazon as well, but specifically Azure because we are co-selling with Microsoft. So we are working on a lot of partnerships with them to work with our clients.
Okay, this explains.
Yeah.
And how would you compare yourself to a system just like CockroachDB?
CockroachDB, I suppose we are working on a benchmarking with that, but like if you talk about InfluxDB, for instance, which is quite similar, I would say that InfluxDB outperforms CrateDB if you have smaller data use cases, but when you have a lot of ingress, as much as like billion data points per second, and you have to increase the number of nodes in a cluster, the linear scalability of CrateDB outperforms by as much as 32 times with similar database solutions.
How much of CrateDB is open source? Is the full stack open source, or is it?
Yeah, so CrateDB is open source and is on GitHub, github.com/crate. And CrateDB Cloud is basically the service that we provide on Azure, but the database is open source.